This wasn't just one shot. November 22nd, 1963, one of the most powerful men in the world was killed in broad daylight. The official story says it was one man, one shooter, one moment. But the deeper you look, the less it makes sense, because some details were never meant to be explained. On November 22nd, 1963, the assassination of President John F. Kennedy was not just a sudden act of violence, but an event that would later be examined as a complex physical and investigative system, one that required reconstruction through geometry, motion, and mechanical constraints rather than simple observation. Because in a matter of seconds, multiple variables came into play, including the position of the presidential motorcade as it moved through Dealey Plaza, the elevation of surrounding structures, and the assumed firing point behind the vehicle, which together created a downward trajectory consistent with the basic principles of projectile motion, where a high-velocity bullet follows a path defined by angle, gravity, and initial direction. And according to the official findings, 3 shots were fired from a bolt-action rifle, a detail that introduced a critical engineering limitation since each shot required manual cycling of the mechanism, meaning that the sequence had to fit within both the mechanical timing of the weapon and the operator's ability to re-aim under pressure. While one of the most debated elements of this reconstruction became the so-called single bullet, a proposed continuous trajectory that depended on precise alignment between the shooter, the moving vehicle, and the individuals inside it. And although such alignment is not impossible from a purely physical standpoint, it relies on exact assumptions about positioning, angle, and timing, which means that even small deviations could significantly alter the outcome, transforming what initially appeared to be a simple explanation into a scenario that becomes increasingly complex when analyzed through the combined lens of physics and engineering. As investigators and analysts moved beyond the initial reconstruction, the focus began to shift toward the relationship between mechanical constraints and human performance, because the operation of a bolt-action rifle inherently introduces delays between shots, requiring the shooter to cycle the mechanism, reacquire the target, and stabilize aim before firing again, all within a limited time window. And when this process is placed within the context of a moving target, the problem evolves into one of dynamic tracking, where both the shooter and the motorcade are constantly changing position relative to each other, introducing variables such as angular displacement, reaction time, visual alignment, and stability under pressure, while also maintaining accuracy over distance, which transforms the question from simple possibility into one of consistency and repeatability. Because performing such actions once under controlled conditions is fundamentally different from executing them in real time during a rapidly unfolding event. And although some controlled tests and reconstructions have demonstrated that the sequence can be completed within the estimated time frame, other analyses suggest that it approaches the upper limits of human capability, making the timing aspect not just a question of whether it could happen, but how reliably it could occur under real-world conditions. Which is why this part of the case remains one of the most technically debated elements even decades later. When the investigation turned toward trajectory analysis, the process required mapping entry and exit points, estimating angles, and aligning those calculations with the spatial configuration of the scene. But unlike controlled laboratory conditions, real-world events introduce uncertainty at every stage because measurements are often incomplete, perspectives vary depending on the observer, and small inaccuracies in position or timing can expand into larger differences in interpretation. And, in the case of the single bullet trajectory, The model depends heavily on the relative positioning of individuals at the exact moment of impact, which is difficult to determine with absolute precision, meaning that multiple configurations can sometimes produce results that appear consistent within acceptable margins of error. And from an engineering perspective, this transforms the problem into one of probabilistic modeling rather than exact reconstruction, where analysts must evaluate which scenario best fits the available evidence while acknowledging that the inputs themselves are not perfectly fixed. And when these uncertainties are combined with witness accounts that differ in perception and timing, the overall reconstruction becomes less about finding a single definitive path and more about understanding the range of physically plausible possibilities. More than half a century later, the assassination of President John F. Kennedy continues to be studied not only because of its historical impact, but because it represents a system that resists complete closure under analytical scrutiny, as high-speed events involving multiple variables, limited data, and human factors rarely resolve into a single, perfectly defined model, even when advanced tools are applied. And while modern simulations can reconstruct trajectories, timing sequences, and mechanical constraints with increasing precision, they still depend on initial conditions that are not fully known, which means that different assumptions can lead to different yet technically plausible outcomes. And this is why the case remains active in analytical discussion. Not necessarily because the known facts are insufficient, but because the relationships between those facts allow for more than one consistent interpretation, making it a rare example where physics, engineering, and investigation intersect without converging into a single, universally accepted conclusion, ensuring that the event continues to be examined, debated, and remembered as both a defining moment in history and an enduring analytical challenge.